Yeah, I think we can get started.
Okay, great. Can you all hear me okay?
Yes, loud and clear.
Okay, sounds good. All right, good afternoon, everyone. My name is Yanbing Wang. I'm assistant professor at Arizona State University. And today I will be hosting this special seminar. It's co-organized by CE 51591, the graduate seminar at ASU, as well as the TBD Center, the Travel Behavior and Demand Center at ASU as well. And today it's my pleasure to introduce our speaker, Zhe Fu. Actually, we call her Fu Zhe because in Chinese, the last name goes first. But anyways, she is a colleague of mine from our shared academic family, and I have had the privilege of seeing her work firsthand, and most notably during our large-scale autonomous vehicle experiment that we conducted together in Nashville, which I'm sure she will talk about that exciting experiment today. Zhe is currently a final year PhD candidate in transportation engineering at UC Berkeley, advised by Professor Alex Bayan at the Berkeley AI Research Lab. Her work focuses on learning, control, and modeling for distributed parameter systems, specifically within mixed autonomy. And she's known for developing physics-informed neural models and validating them through large-scale field experiments. And she has brought an impressive track record, including being named the 2025 ENO Fellow by the Federal Highway Administration, as well as a rising star in not only just one, but three disciplines in mechanical engineering, electrical engineering, computer science, as well as cyber physical systems. So she has a lot of meaningful and insightful work to share with us today. So please join me in welcoming Zhe Fu. And also, before we get started, I just wanted to ask for people who have questions, do you prefer, Zhe, do you prefer people to interrupt you right away or save that towards the end of the talk?
Actually, thank you so much for asking that. I actually prefer the talk to be more interactive. So feel free to interrupt me right away. And like if it is a quick like clarification question, I'm super happy to like resolve it right away. And if it is more towards kind of like research future direction discussion, then I will like prefer to save it at the end of the talk.
Okay, sounds good. Yeah, so short questions interrupt her, and then long questions save to the end. All right, and with that cleared up, I think we can get started.
Thank you so much, Professor Wang. And it's a great like introduction of me. Like, thank you so much for inviting me to this exciting seminar co-hosted by like both ASU Interdisciplinary Seminar and the TBD Center. Let me share my screen. Can you see my screen right now?
Yes, we can see your desktop.
How about now? Like, can you
Yes,
see
yes, I can
the
see the
slide?
slides. Perfect.
Okay, great, great, great. All right, let's get it started. Hello, everyone. My name is Zhe Fu. I'm a final year PhD candidate at UC Berkeley, and today is my great honor to present you some of my PhD work. It's about like physics-informed learning and control for mixed autonomous systems, and specifically, I will use what Professor Wang just introduced, our like large scale like scientific mixed autonomy project as an example to talk about like my methodology applied to the traffic smoothing. So like before I dive into that, I want to give you a short introduction about what is mixed autonomy. So mixed autonomy is not a future scenario. It's already here. And unfortunately, initially I designed to kind of want to have like a quick survey, but like it's a little bit hard to conduct it online. But like I'm pretty sure most of you have already seen autonomous vehicles like Waymo Cruise, and even like you have never taken that, I believe for your own vehicles or when you take Uber or Lyft, there are a lot of like vehicles already have like cruise control, lane keeping, adaptive cruise control, those autonomous assistant systems. So like on the road, we already see both automated and human-driven vehicles. And in the air, there are also like drone fleets that operate side by side with piloted drones. And if we move forward to urban air mobility, we'll likely see both piloted and unpiloted air taxis coexisting in the same airspace. But like despite this like advance, the operation of like mixed autonomy system is inherently complex. And that complexity shows up at several different layers. So first of all, at the autonomy layer, most agents are only like partially automated, and the number of automated vehicles is still limited. Moreover, these automated systems have heterogeneous like sensing and actuation capabilities, like different sensors, different control interface, and different levels of responsiveness. And besides that, on the human behavior layer, we face an uncertainty and the variability of human actions. Like drivers and pilots make decisions based on experience, perception, and personal comfort, which are difficult to model or predict. And finally, like at the interaction layer, we see heterogeneous coupling between human and automated agents, each reacting differently to one another, creating feedback loops and emergent behavior at the system level. So altogether, these factors makes mixed autonomy system very challenging to model, predict, and control. So addressing these like challenges requires an approach that is both theoretically grounded and systematically integrated. So what do I mean theoretically grounded? My approach is what I call like model-informed learning, which means embedding physical principles and structural models into learning to achieve both interpretability and data efficiency. So let's take a step back. Like in today's data-driven area, it's tempting to think we can solve every problem by just collecting more data and training like larger models. But pure data-driven learning has clear limitations. It demands huge amounts of data and computational resources. It often lacks interpretability or physical like consistency, and it's generalized really poorly when facing new or noisy like environments. Yet, but before the area of large-scale computation, we already have like centers of physical and behavioral modeling, like governing laws, conservation equations, structure priors, and all the analytical models. And so instead of discarding all these models, why not integrate them? So by combining the expressiveness of data-driven learning with discipline of physical and structural modeling, we can build models that are more like data efficient, interpretable, and generalizable. On the other hand, I believe that in complex systems, for example, the mixed autonomy systems, or like our general like mobility systems, to make a real impact, we need to co-design. And what do I mean by that? So instead of treating modeling, control, and experimentation as separate stages, where like one comes after another, I view them as parts of like closed loop systems that like evolve all together. So modeling like informs control design, and control design derived to the experimentation, and experimentation generates feedback and all the field data, while the field data in turns refine the modeling. So this continuous loop is what I call like co-design. Each component evolves in the united pipeline within the physical system. So at a high level, my research is grounded in a model-informed co-design philosophy, and I view complex cyber-physics systems as requiring this like three components. And during my PhD, my work spans all these three layers. And here is a brief research summary. On the modeling side, I combine numerical analysis and machine learning to model large-scale systems such as energy consumption and traffic flow. And on the control side, I mainly use control theory and deep learning to design algorithms that steer the system toward desired behaviors. For example, I use control theory together to like develop wave dissipating controllers for traffic, and also safety guaranteeing strategies based on control barrier functions, and anomaly detection schemes, and smart charging optimizations. And on the experimentation side, I validate these ideas in practice and collect valuable data. This includes the 100 automated vehicles field test circles. That's the project that Professor Wang mentioned at the very beginning. And I also like use some other use a Cadillac XT5 as a mobile data collector to record stop-and-go waves in the Bay Area. And I also participate in a BMW smart charging pilot that provided rich real-world charging data. So, but for today, due to the time constraint, I want to mainly focus on a topic about like traffic smoothing, and I want to highlight the core theme, which is achieving system efficiency through a few automated agents in mixed autonomy traffic. So just give you a little bit background. Like one common traffic inefficiency in our like current like ground traffic system is the stop and go waves. And those stop and go waves actually emerge without any bottlenecks or accidents or like infrastructure stuff. It's purely from human reaction and delay. And so our goal is to exactly try to dissipate those inefficiency. And the method is mostly we aim to use only a few partially automated vehicles to kind of like dissipate the stop and go waves, but with the constraints of still maintaining the overall throughput. So we don't want to harm the current traffic efficiency of the highway. And so like for this specific research question, our logic is that we treat those automated vehicles as robot managers within the system, and we will deploy some control on top of that. And those cars will kind of have some influence for the rest of the car that following it. So it sounds like chauffeur, the human-driven vehicles behind it. And for this goal, we actually follow the co-design structure that I like motivated at the very beginning in terms of modeling, control, and experimentation. So for the modeling part, the main idea is that we want to understand the dynamics of the current system we're tackling with so that we can gain some traffic state estimation, and so that like, for example, what's going on in the downstream. And then that would be a super helpful information for us for the downstream control layer, so that we can design a target speed that planning for a smooth speed profile for the vehicles to like drive with. And in the end, we wanted to deploy that onto the few automated vehicles that we have the control on, so that it can behave like a leader to shuffling the human drivers behind it. So this I want to like give you some sense about what is the harness and what is the solution for each of the layer. For modeling part, the main difficulty for this like traffic systems is that the traffic wave is actually contains a lot of discontinuities, and at the same time we might have like very limited data. So like the solution we propose for this part of the problem is we develop a new physics-informed neural solvers, and we call it NFVM. And for the control layer, the problem for this is mostly about for the few automated vehicles that we can control is still partially autonomous. It's not like full autonomous vehicles. And also it varies from different manufacturers. So it has we need to deal with the heterogeneous between all of them. And for that, I propose like two different control strategies. One is more based on kernel-based planner, and the other one is the imitation learning control. And on the experimentation side, when we try to deploy all those like control strategy on real car, some like communication delay would come, and also there's a huge sim to real gap. And the solution that we propose is to like try to do more like model validated and feedback loop deployment. So like let's dive into the first module, the modeling part. I think I will give you like a first like sense of like what we really did here, like a summary, and then I will dive into the details. So I want to point out that like the technical innovation here is that different from the previous physics-informed machine learning approaches, which is adding the PDE structure directly into the loss function. We actually keep the core finite volume method structure to hard preserve the conservation loss, but use like a neural network to approximate the numerical flux. And this design achieved many like crucial results. So the solver that we developed can outperform all known finite volume numerical schemes across multiple hyperbolic PDE models and multiple noisy traffic field data. And importantly, it matches the computational cost of first order finite volume schemes. And this, so this is like a solver, but like in the end, when we try to like apply that and like make it useful, is it can provide an accurate and robust tool for traffic state estimation and predictions, which support our further simulation and control design. So let's dive into the details of that. I believe like everybody here who are like doing transportation related research are quite familiar with those models to like describe our traffic flow dynamics. But like still want to like highlight it, like 7 years ago already, like people proposed the LWR model, which is an elegant first order PDE scalar model to describe the dynamics. And later, like people add on some more equations in terms of momentum, describing the momentums, and also like expand the current like 1D into like 2D, for example, the ARZ model. But like all of them together, they are all hyperbolic PDEs. And these hyperbolic PDEs are super hard to solve. Why? Because these PDEs create troublesome solutions like shocks and discontinuities. And moreover, like mathematically, there are infinitely many possible weak solutions, while only the entropy solution is physically valid. And specifically finding that entropy solution is very challenging. And traditionally, we use like finite volume methods to solve these hyperbolic equations. However, this classical like numerical like solvers tend to oversmooth shocks. For example, on the left-hand side, you can see like the Lux-Friedrichs, which is a very like famous finite volume solver. At the like discontinuities here, it's definitely like oversmooth too much. And so this motivates us with the question like, can we design a neural network-based solver that match or even surpass the traditional finite volume methods in accuracy while still keeping the cost low, like the computational cost low? And so like for the current neural net, we did like a kind of like literature review to kind of see what's the current existing neural network solvers. But like those solvers tends to struggle with preserving the regularity and also entropy conditions and conservation loss. So like we are thinking, okay, for our like new solver, what are the properties that we wanted to have? First of all, we wanted to preserve essential the PDE properties. And then we wanted to be efficient that can matches the computational cost of finite volume schemes. And also, we already use a neural network. We want to kind of take advantage of that. We want our solver to have like flexible architecture, supports both like supervised and unsupervised learning. And we want it to kind of flexible and generalizable, extensible to higher order like space and time, and also not just focusing on synthetic PDE data, but can literally like apply to the field and like apply on the real world data. So before I introduce our method, which is the NFVM, Neural Finite Volume Method, let's quickly revisit the finite volume method, since our architecture is designed to mirror the FVM-like structure. So for FVM, we discretize space and time into small cells. And within each cell, we track the average value of the solution. And here we use density as an example. And then like using the conservation law, we update the value in each cell at the next time step. And this update depends on the numerical flux, which captures how much stuff flows across the cell boundary. And specifically for a first order finite volume method, we only need 3 cells as input, the left, middle, and right. And based on this, we apply the fixed update rule derived from the conservation to compute the density of the center cell at the next time step. And so like, now here is the key shift that defines our method. So in the classical like finite volume method, the core of the update is the numerical flux. And that is usually a function like designed by hand, like the Goodenough scheme as we illustrated here. So what we propose is using a neural network to replace this handcrafted flux approximations. And in first order scheme, it takes in the density of the 2 adjacent cells and it outputs a learned approximation of the flux across their boundary. So I guess like those are kind of still too abstract to me. So I'll show you how our method works with those illustrations. So on the left-hand side is like a segment of a highway, and we can discretize them into different cells. And space-wise, our neural network takes neighboring densities and computes flux locally. For example, here we obtain the numerical flux between cell 3 and cell 4. And with the neural network, we got it, and then we put into the update rule. And at the same time, we can also obtain the numerical flux between cell 2 and cell 3 to fit it back into the update rule. And then we can get the density of like cell 3 at the next time step. And this process can be conducted simultaneously across the space at the same time step. Over time, we update the cell densities exactly like in the traditional finite volume method. At the initial time step, we obtain the numerical flux across the space from our neural network. And then we obtain the next time steps density with the update rule. And then we need to fill in the boundary condition here. And the procedure continues as the previous time step. Then we do it step by step until we obtain all the forecast. So now you might have already get our like framework from the high level, but what did we use the neural network for, like the numerical flux approximation? In this work, we use a surprisingly small convolutional neural network, which contains less than like 1,200 parameters. And our framework can support both supervised and unsupervised learning. In supervised NFVM, we trained on a bunch of Riemann problems. Those are the initial value problems with 2 constant states separated by discontinuity. And there are simple cases which have explicit solutions, either like shock waves or refractions as shown. And we train on many of these like simple cases, but later we validate them on much more complex conditions. However, like in many cases, we won't have access to the exact solutions to the PDE that we're trying to solve. Therefore, we developed the unsupervised scheme, which learns from physics directly via a weak formulation loss with a set of suitable test functions. And the loss measures how well we respect the PDE. And in our test, we use a set of compactly supported polynomials as the test functions. And it was trained on many random Riemann initial conditions, but this time we don't know about the solutions. Now you already learned the framework and the neural structure of our method. Let's take a look at how our method performs. So initially for the synthetic PDE data, we picked at two well-suited categories of hyperbolic PDEs as the benchmark problems. The first family is the LWR model, and the other one is the implicit Berger's equation. And one thing I need to point out is that for LWR model, it contains the flux function in the PDE, which reflected our concept of the fundamental diagram. And I guess it's people who have the transportation background already knows that we have several different ways to fit in the flux function, and there are varies from each other. And actually, if we plug in different flux function to the PDE, it ends as a different variant of the PDE itself. And for this work, we specifically take a look at the green shell flux function, Greenberg, trapezoidal, underwood, triangular, and also a skewed triangular. And now let's first take a look at how our method perform on those benchmark PDE problems. As I mentioned before, we train only on very simple Riemann problems, but we validate them on much more complex initial conditions. And what I show here is the ground truth and our method prediction comparing on two different complex initial conditions. And visually, it matches with the ground truth. And besides the visual stuff, I also want to give you some quantitative results. So we run validation on all 7 different PDEs, and each PDE across 1,000 complex initial conditions. And we compute the average L2 error for each of the model, including our method for supervised version and unsupervised version. And we compare them with first of all, the first group is the first order final volume schemes, and it can beat all of them. And the good enough is among all 3 of them, it performs the best. And we also compare with the higher order final volume schemes, including ENO and WINO. And the results again shows that we can rival with the accuracy of the higher order final volume scheme. And one interesting thing I want to emphasize here is we also pick a finite element method, which is the discontinuous Galerkin. And this is a very well-known method for improving the accuracy, but it will incur a huge high computational cost. And also the implementation of that is way more complicated than most of the final volume schemes. And for here, as you can see, our accuracy cannot match with DG yet, but spoiler alert, later I will introduce you our extension version of the method, and it surprisingly can actually match with the DG. This is just a more intuitive way to view the quantitative results that we introduced the win rate comparison. So the win rate here, definition is number of the evaluation set that row schemes outperforms the column schemes. And again, as I said before, on different flux function, different PDE, it shows that our method can easily beat the first order final volume schemes, rival with the higher order final volume schemes, while in terms of accuracy for now, the Valina version cannot beat with DG yet. And besides the accuracy comparison, I also want to show you some exciting results about the convergency. And here we compare both our supervised and unsupervised schemes with good enough, which is proven to be converged to entropy solution. And as the time discretization goes smaller and smaller, both our scheme, the supervised and unsupervised, consistently obtain less error and converge faster than good enough, which shows that empirically our method can converge to our entropy solution. And as I mentioned before, another advantage of our method is we can easily extend and incorporate way more flexible structure of the input. And so that's we just easily extend the input for instead of just the 3 stencils and 1 time step to 5 stencils and 5 time steps, or even more in the later stage. But here I just want to show you that I use 5 times 5 as an example. And all we need to do is kind of just change the structure of the input while still going through our neural network, and it will output approximation of the numerical flux, and the rest of the steps would be exactly the same. For here, it's the first window here, and then we can shift and obtain the other numerical flux, and so on and so forth. And so then the question will come okay, you extend your input, how much computational cost you increase by that? And to be honest, when we do that, extend from the vanilla NFVM to 5 times 5, it's not that much parameters increase. Even for here, it's just less than 1,600 parameters in total. And but actually it performs surprisingly well. And here I show you the results on both Berger's equation and LWR triangular equation. Previously, we are much closer to good enough, which is one of the first order finite volume scheme. But now we are much closer to the exact solution, which is the black line over here. And even over long evolutions, NVM consistently tracks the exact solutions, clearly surpassing the baseline, the good enough. And I would also love to give you some quantitative results here. So among all the tests we did, now the 5-5 variant actually can have the same skill comparing with the DG, which is previously significantly achieving better accuracy than our vanilla version and the rest of the finite volume schemes. And besides those PDE synthetic data benchmarks, I also want to show you that how our method performs on the real world data. So for here, we start with drone capture highway data, B3D data set that collected by our lab, led by our previous lab mate, Fengyu Wu. And that data set contains 12 videos recorded by a drone above a highway. And it contains 15 minutes of the data. And for here, you can see 4 visible stop and go waves. And for this plot, it's more visible. We colored it with the density and the waves and the direction of the free flow is more visible here. And we trained only on the last wave, which is 70 seconds of the whole data set, which compose only 8% of the data set. And then we evaluate that on the first 800 seconds, which is the remaining 92% of the data. And before I show you how our method behave, I want to give you a understanding what are those traditional numerical solvers behave here. So as you can see, we try to fit in different flux function, but still all of them performs pretty bad. And on the right hand side is the ground truth, and on the left hand side is different method with different flux function. It's just generating, vaguely trying to capture the shape of the wave. And here we just pick the best final volume method results that we can obtain, which is from the Wino scheme with the triangular flux function here. And as you can see, like at the very beginning, it's just predicts something really weird. And while like our Verlina NFVM also kind of like, I think it's because of this, like it's trying to like it failed to like predict the dissipation of the wave here. But with the enhanced version, like with more stencil and more time step, our method actually can correctly like capture the dissipation of the wave. And also one notification is like one thing that I need to highlight is we also correctly predict the free flow like directions here. And so like that is like a kind of short like quick overview of our like method in terms of how we try to model the traffic dynamics and how it can actually realize and achieve the task of the prediction of the traffic. And I want to actually pause a little bit here in case anybody have some questions for this first part. If it's not, then I will like proceed to the next module, which is in terms of the control.
I don't see any questions so far, so please continue.
Okay, sounds good. Okay, and then like with that tool, like with the understanding of the traffic dynamics, I would love to like kind of think about how we can like do something and kind of like insert some intervention of the system so that we can help the system to solve some practical problem or to improve the system efficiency and performance. And in this specific traffic smoothing task, as I mentioned, our like challenge is about like we only have limited amount of like control on top of the actuator that we can have, and also for among them it's also have some partially observability and control. And just want to give you a kind of quick like dragging you back from the topic is like our current mixed autonomy stage is have in terms of the automation level, it's mostly like level 2, which is adaptive cruise control, not the fully autonomous vehicles. And on the coordination level, only few automated vehicles are available on the road. And on the system level, there are heterogeneous automation, which means like different cars might have different sensing and different actuation abilities because it's produced by different OEM. And just want to quickly remind you, like the question we are trying to tackle here is, can we utilize this limited number of partially automated and heterogeneous vehicles to stabilize traffic conditions for all vehicles, not just those vehicles that we can control within the systems? And from my like perspective, I actually propose 2 different control strategies or algorithms under different sensing and actuation paradigms. The first one is a kernel-based planner, and it is using color planning for target speed design. And the other one is the imitation learning control, which is mimicking the optimal driving behavior under uncertainty. And but both this 2 is trying to, first of all, like based on the information collected from the road and also the information we obtain from the previous layer, like the modeling part that we know the traffic state, we want, like, as you can see on the plot here for those orange like curve here, we actually want to, after applying those control strategy, obtain a smooth speed profile. And we like with this 2 control strategy, I validated them both in simulation with the real traffic trajectories. And in summary, with just 4% of AV penetration, we can already achieve over 15% energy saving for the whole system. That's like in the simulation. And so like that's gave you like a high level picture of this piece of the work. And I will dive a little bit into the details. And to better understand my control algorithms, I would love to like set up some problem setting here. Take a look at this like single lane highway, and there are a bunch of like vehicles like following each other. And for those like red cars are the car that we are trying to control. Those are the control automated vehicles. And those vehicles have the radar, so it can sense what's going on for the leader vehicle. And we marked this leader vehicle as sensed human-driven vehicles as blue vehicles. And for the rest of the vehicles, they're all white vehicles. We mark it as white, and they're all human-driven vehicles that we don't have the ability to control, and we also don't have the ability to sense it. And I also would love to like point out that like we define some different sensing paradigm. For global sensing, we are saying that under that paradigm, we will have both the ego states, which is the red vehicle's position and the speed, and also the leader state. And besides that, some traffic state estimation that we can obtain. And they're like, not like every like road is ideal that we can have the traffic state estimation. So in some cases, we only have local sensing, which is just our control vehicles information and obtained from the leader vehicles. And so that's exactly motivates my two control algorithms. And they are actually follow kind of the philosophy of teacher to student, why I say that. So under the global sensing, the ideal cases, we have like three category of the inputs, and the control like structure would like this, the input, and then we wish after passing our control algorithm, we will obtain a smooth actions that can help us to smooth the traffic. And specifically for here, the structure that I apply is mostly about the kernel planning. But like under local sensing, which means we lose the access to the TSE, with still thinking, okay, is there a way for us to just rely on the local information, but still produce a similar performance like of the actions comparing to the global sensing one? So the idea is that I actually treat my global sensing algorithm as the teacher and like kind of mimic. That's why I call it like the imitation learning control. Mimic whatever it is doing so that it can generate a bunch of the actions that still match with the previous abundant information. And a little bit more detail about the kernel-based feedback control architecture here. It's actually a hierarchical control. On the top, like higher layer, the idea is that we have some like traffic state estimation, and we know that maybe in the future 1,000 kilometers there you have to slow down. Then instead of like you drive it right away over there and then like stop, you can actually plan it ahead, like decelerate smoothly. And that like exactly is how this like V-target serves. And it's exactly like trying to like aggregate the information from the TSE and gave you a high level signal saying that, okay, at this position, you are probably be better to drive at this speed. But because those information are like really like high level, like loose granularity, if we just directly apply that speed, possibly like it's ignored what is feasible locally. So that's why we equip that with the lower layer, which is a PD controller that can do the gap regulation, and also equip that with the safety filter. So like the kernel-based feedback control is more like the structure is like this. While like as I mentioned before, like not in every case we are perfectly have the TSE. So like the question would come as like, how can we just use the local sensing to stabilize it? And like trying to design a strategy that kind of like get rid of the reliance of the TSE. And so that motivates me about like, okay, how about we use imitation learning? I know like in autonomous driving, like literature, imitation learning has been used for many times, but most of them are just trying to mimic whatever the human behaviors are. So for here, the innovation is that instead of we treat the human behaviors, we treat expert policy, a previous developed algorithm as the expert to mimic with, while like here the main goal is to get rid of some like reliance of the input. And for like our method, we apply the Dagger algorithm in the training process, treating those like global sensing control strategies as expert to reduce the reliance on the global sensing. And we first initialize our demonstration sets and policy and collect experts' actions. In our case, is the like a kernel control. And then we augment our state action pairs data sets with the collected pairs. And this augmentation and online query can help us to alleviate a common problem in imitation learning, the covariance shift. So that's a brief introduction in terms of the two control strategy that I designed for different sensing paradigm. And we firstly validate that into the simulation, and we train and evaluate in two different cases. First, we take a look at a single lane setting and build our own simulator by treating the recorded trajectories, stop and go trajectories obtained from the highway. And on the right-hand side is an example of the time-space diagram generated from our simulator. And actually in that, like each of the line represent one vehicle. And I think this is generated with like 200 vehicles. And we also trained on multi-lane setting where we build a like I-210 network in Sumo, open source, like Sumo, like an open source like traffic simulator. And for these cases, it's multi-lane, and we want to generate stop and go waves by imbalanced inflow and outflow. Here I show you some numerical results to evaluate both our methods. So for case one, which is just a single lane, we choose 10 different scenarios to simulate with, and those can be categorized into light or moderate congestion and heavy congestion. And for the light, like and moderate congestion, our global sensing, which is the kernel-based controller, can achieve overall like 16.57% of energy saving. So here we use the energy consumption as a proxy of the smoothness of the traffic flow. And for the imitation learning strategy, it can also like achieve the similar like performance comparing to the kernel-based. And to give you a little bit more details about that, on the left-hand side is a case that there's no control applied at all. And in the middle is our kernel-based control, and on the right-hand side is the imitation learning control. As you can see here, like the significant like congestion area, both our two strategies actually smooth out this like black area, and specifically take a look at those speed profile. At the very beginning, like without any control here, you can see this like vehicle's speed oscillation actually amplified along the time, while after we apply our control strategy here, both of them kind of eliminate the amplification of this oscillation. And even for imitation learning here, it's actually shrink a little bit. And for case two, for the multi-lane cases, we actually randomize and enlarge our training domain by playing between different inflow and outflow. And each of the plot shows one scenario that we are testing on. And we actually only pick those have like significant stop and go wave scenario to train on. And this allows the system to learn to match behaviors that dissipate waves as opposite to overfit into a specific like speed. And like here is an animation to show you like the comparison without control and with control. And this is only with like 5% of the AV penetration. And as you can see on the bottom, the flow actually drive significantly smoother comparing to the upper. And we evaluated also with some quantitative result, but here I don't want you to focus on the number here. Just take a look at the color. So the red, the more red it is, means the more like increase we have compared to the baseline, while versus for the blue, the more blue it is, means it is like more decrease comparing to the baseline. And we test firstly with the energy efficiency. As you can see, both two strategy can increase the energy efficiency comparing to no control. While for acceleration, we definitely wanted to have like less acceleration. So again, it's bluish and shows us that it decreased comparing to the baseline. While at the very beginning, I have mentioned all the control that we apply is within the constraint that we want to not harm the traffic system efficiency. And the outflow rate here is like kept as the grayish. So like we minimally like trying to like influence the outflow rate here. So like this success in simulation led to the validation in a large operational field test, and which is the CIRCLES project. And the CIRCLES project, which is the largest mixed traffic field experiment today, we deployed like 100 automated vehicles on the I-24 highway. And this is a national scale like collaboration project showcasing including like the NSF, DOE, the DOT, and like many industry partners that kindly sponsor us with the car that we control from Toyota, Nissan, and GM. And it's collaborated with 4 universities. And specifically, we deploy that on the I-24 highway because over there is a really amazing project, and Professor Wang used to be part of it. It's the I-24 motion. That's like testbed provides like over 200 really high resolution cameras along the highway, and it can like provide us with the all the footage of the cars that passing by that highway, because like the goal of the project is not just to evaluate what the performance of our control vehicles. We are more curious about like how these few automated vehicles can impact the whole systems. So we have a need to capture all the trajectories and the performance of all the other human-driven vehicles, while we don't have any monitor on their cars. So we need like those cameras to capture all of them, and like so that we can further analyze the performance of the system. And so that test is a team efforts and like a great coordination among 50 researchers, and it include tons of different tasks, including like algorithm refine, hardware deployment, management, etc. And my contribution in this project is I help design the core control algorithms and support the energy modeling and evaluation, and deploy the controller on hardware and cars, and also support the experimental logistics. To give you a little bit of sense of how this like test is worked, I will like illustrate you with one typical day during the test week. Oh, by the way, yes, like we conducted the experiment for a whole week. And among like a typical day, I usually arrive at the parking lot, the headquarters at like 5 a.m. to trying to do the gear check for the driver for each of the car, and sending them out as like this like slow video shows. You can see those vehicles at the headquarters just like departing one by one, and then like they will come back one by one. And after sending all them out, I will go back to the headquarters to monitor the test and detect potential bugs within my algorithm. And then after the test is concluded, I will try to refine the algorithm and improve the controllers. And then in the afternoon, early afternoon, we will pick a few test cars and try to deploy the refined algorithm to see how it works. And it usually requires several rounds of iterations. And then in the late night, we will finally deploy the finalized controller for the other day to test on all 100 automated cars. So we collected the vehicles trajectories and analyzed the fuel economy based on that. And we found that with less than 2% of AV penetration, we actually can achieve over 10% measured system-wide energy savings. And the right plot also shows that the fuel consumption versus their distance to nearest controlled automated vehicle. And we find that the nearer the human-driven vehicles to the AVR, the more fuel efficiency they could gain, which also shows our control strategy helps smooth traffic and save fuel. And besides that, with all those trajectories, thanks for the I-24 motion team again, we can generate maybe the largest time-space diagram in the world till now. And it spans 4 miles and I think even more than 4 hours. And one thing that I need to mention here is each of the white line here represent one of the car that we have the ability to control. And this plot is generated from one of the test day. And I want to also mention that with this abundant data set, we actually can do a lot of other things, including closing the loop, which is we can use those data to further refine our modeling tool, as I proposed at the very beginning, to do a co-design for tackling the problems within this mixed autonomy complex systems. And so I believe I-24 motion team already released a public data set, which is including over 600,000 vehicle trajectories. And with this data set, we applied our NFVM with the first hour of one of the day, which just composed of 2.5% of the data set as the training set. And we validate that for the rest of the data. First of all, for the prediction task on the training day, in the middle is another variant of our NFVM method. For here, we use actually 11 stencils, baseband stencils, and 11 time steps. And on the right-hand side is the good enough scheme treated as a baseline, which is as I mentioned before, first order final volume schemes. And clearly you can see our method kind of match with the wave shape. And also we successfully predict the dissipation of the wave, while good enough failed to do that. And we also just directly use this model to predict those unseen days. As you can see on the left-hand side, the ground truth, they're behave varies from the train day that we have, but our method still performs pretty well comparing to the baseline. So yeah, that's just a free a short teaser in terms of this piece of the work, but I think it's already gave you a sense of how the whole co-design loop is going through in terms of the topic of traffic smoothing. So I would love to end my talk here, and thank you so much for your attention. And I also want to thank you for thanks to my main contributors among all these amazing collaborators, students. And I also have the privilege to collaborate with many different professors and PIs for this project. And I would also love to acknowledge the funding resources during my PhD. And thank you so much. And I'm happy to answer any question.
Thank you, Joe. This is super impressive. I guess I only understand a little bit of your work earlier, but it's so nice to see everything get tied together. So I guess we have maybe around 5 minutes left for questions. Because I cannot really see the audience in person, I would direct maybe to Professor Angeli, Jamie, or Fan to acquaint you with the question. But for people online, if you have any questions, please feel free to raise your hands or put them in the chat.
Any questions in person?
I'll take a stab, and please forgive me. I'm a pavement materials engineer by trade. But I was just curious. It was interesting that you found that the nearer the regular vehicle fueled, I don't remember human-driven vehicles to the AV, the more fuel efficiency. I was wondering if you can talk about that, and if does that have to relate with the aerodynamics of being behind a vehicle? But if you could talk about this finding, it's quite interesting.
Yeah, of course, that's a really a good question. So I think that relates to the core logic of the control within this project. So I will illustrate that in a better way. So the core idea here is that when you drive on the highway, especially when you are in congestion, you have the tendency to follow whatever your lead vehicle do. If the lead vehicle stop, you will have to stop, otherwise you will crash to it, right? But if the lead vehicle accelerate, you have the tendency to also accelerate. So the whole idea of the control is if we control your lead vehicle, we have some power of control you in the same way. But then intuitively is the closer you are to the vehicle that we actually control, maybe the way you mimic the speed that we deploy on the car will be closer. So that's power of influence just decrease when you are further far away from the lead vehicle. So that would be my explanation. But I do think maybe it's slightly related to the aerodynamics, but I think the impact here might be not that significant.
Yeah, no, that makes sense. Any other questions? I don't see any. Let me see.
So I actually have a question, Joe. And also curious about your intuitive understanding, or give us some intuitive explanation in terms of how having the autonomous vehicles in the flow with interacting with all the other human-driven vehicles. Do you see the human-driven vehicles' behavior necessarily change as the penetration rate of autonomous vehicles increase? Or are current studies pretty much assuming that the human behaviors don't change? I guess I'm just curious to hear your intuition in terms of will this result carry out in the real world when human behaviors actually change or interact with the different control strategies?
That's a really excellent question. I would in short, I would say I observe both ways. So for example, in this task, test or circles project, we actually use the market sell car, the Toyota, Nissan, and GM cars on the road. So they looks exactly the same as all the other vehicles. So I think those human drivers even didn't notice they are the test cars at all. So I think in that case, they won't treat those cars differently. But I do see, for example, in San Francisco, I saw those Waymo's crews running on the way, and then some human drivers will deliberately bully those cars. It's definitely changed their behavior, they might deliberately cut in for those cars, or some drivers will be more conservative. They will just see those cars, I don't trust those cars, I will leave even larger gap towards them. So I would say if we just want to do smooth traffic smoothing, we even don't need to specifically deploy on some of the cars. We can even just have an app and tell the human drivers, okay, at this location, I would suggest you to drive in this speed. And then we can still achieve some like efficiency from that. And but like if the topic turns to like how autonomous vehicles or how those automated vehicles would impact the human behavior, I think it really depends on whether they are visible and how human feels about that. It can be more conservative and it can be like more aggressive.
Yeah, that's a really interesting point. Like if the control vehicle can be disguised amongst human, then maybe the behavior will be slightly less as compared to if they know that there are autonomous vehicles already.
Yes, I agree.
All right. Any other questions from the audience? If
Maybe
not,
sorry, Andy. Just one small one, and I think it'll be interesting for the students to also understand. I guess walk us through how are you able to do the breakdown of your testing and evaluation at such like a very stark, sharp cut. Like you mentioned, 92% were taken out of testing, right? Compared to like the conventional Pareto principle, where 80% is for testing. So I guess walk us through how are you able to do that, and what are some considerations that students can be mindful of when they're parsing data like this in training, testing, and validation?
Yeah, I would love to do that. So I agree that like for the traditional like machine learning task, we usually just like divide that into like eight or like 80% and 20%, or even like divide that like into like training, validation, and testing. But for here, I think we are more oriented to our terminal goal. So this one is referring to the modeling part. We want to validate how powerful our solver, our method is. And as I mentioned before, our goal is we want to use as little data as we can to show that we don't need that much like computational cost while still achieving satisfactory like performance. So that's why we only pick like very small chunk of data, even less than like traditional 20% or 10%. And also, I think it makes sense that like the whole data set contains 4 different waves. And initially we designed that, we think that, okay, let's grab just one wave and test on the rest of the 3-way and also the free flow. So I think it really depends on what you want to achieve in this specific task and what are the real data set looks like.
Thank you so much. Yanbing, I'll yield to you.
I think that's it. Maybe for the last 1 minute, Zhe, if there's anything that you would like to add or say to the audience before we end.
I would say like thank you so much for coming and like raising those really insightful questions, and feel free to like reach out to me if you have follow-up questions, and I can share my like emails and also my website if you need.
Thank you so much, Zhe. This is a great presentation, and I really appreciate you coming, sharing with us. And yeah, thank you for everyone who joining online and in person today.
Thank you so much. Have a nice day.
Have a good one. Thank you. Bye.